I want to give you an example of an application of oxygen isotope thermometry in metamorphic rocks that I've used in a research project of my own. And this example comes from the Marun-Keu Complex in the polar Ural Mountains of Russia. Here are the polar Ural Mountains, and where they're located is several hundred kilometers east of Moscow. It's a Paleozoic mountain belt. It hasn't been active for hundreds of millions of years. The Marun-Keu Complex is located to the far north near the Kara and Barents Seas, and it's situated within the footwall of the main Uralian fault. This is a normal fault that helped to exhume the high-grade rocks in the Marun-Keu Complex. The main Uralian fault was originally a thrust fault that was active during the time that Eastern Europe and Siberia were colliding about 380 million years ago. The complex itself is comprised of quartzo-feldspathic gneisses that include bodies of eclogite and amphibolite. There are ultramafic rocks to the east in the hanging wall of the main Uralian fault that were exhumed within the suture zone during the collision. The Marun-Keu complex is actually one of several eclogite-bearing subduction zone complexes that were exhumed along the main Uralian fault during the collision that formed the Urals. They all contain blue schists and or eclogites that are high-pressure, low-temperature rocks that form within subduction zones. And the Marun-Keu complex is interesting in part because it contains rocks that are partially transformed or partially metamorphosed, or you could say metasomatized, which involves a chemical change that happens when fluids infiltrate rocks and transform them. There are several places within Marun-Keu where we see amphibolites that is transformed to eclogite. So you can see the amphibolite with the dark black hornblende spotted with garnets here and there, and the eclogite that contains green omphacite and red garnets. These rocks were originally amphibolite, and locally where fractures cut across the amphibolites, the fractures introduced fluids into the rocks, and the rocks were transformed to eclogite. Another set of rocks were formerly gabbro, so you see the white feldspar, and those were transformed also to eclogite, and again you see the red garnets and green omphacites. Those two were fractured and had fluids introduced that allowed the rocks to be transformed to eclogites. And what this suggests is that the rocks were metastable at eclogite facies conditions, meaning they were at the right pressure and temperature conditions to form eclogite, but they had not transformed because of some kinetic barrier. And in this case, it was the addition of fluids that were necessary to actually metamorphose the amphiboles and the garnets to omphacite and garnet. Some might ask whether deformation was in part responsible for the transformation of these rocks. And a student of mine used electron backscatter diffraction to study different minerals within the amphibolites and gabbros and eclogite to determine whether minerals showed evidence of deformation and what temperatures deformation might have taken place at. And in this example, she looked at omphacite that is present in both the amphibolite domain and the eclogite domain in these rocks. And what she found was the C-axes and the A-axes aligned in a pattern in the amphibolite domain, but that were absent in both the transitional part of those rocks and within the eclogite domain. You don't see the same kind of what we call a girdle across these pole figures, and you can think of those as kind of stereo nets. So, had a pre-existing fabric within the amphibolite, but that deformation wasn't involved in transforming the amphibolite to eclogite. This is a schematic showing the starting rock, whether it was amphibolite or gabbro, and the fractures that cut across these rocks. And these arrows indicate a transfer of either sodium and aluminum toward the fracture zone, or of magnesium and perhaps calcium, carbon, and hydrogen to the starting rock. And the point is that fractures cut across the rocks, fluids were able to infiltrate the rock, and then we have this zone of metasomatism or metamorphism of the original starting rock. So over just a few centimeters, notice the scale here, those fluids allowed new, stable eclogite facies minerals to grow. A previous study actually looked at these same rocks using rubidium and strontium isotopes to both calculate ages for the rocks and also to look at the isotopic equilibrium within those isotope systems. And what we found is that the eclogite facies vein had an initial strontium ratio of just over 0.706 and equilibrium between omphacite, white mica in the vein and white mica in the eclogite. In the eclogite and garnet amphibolite, we see an initial strontium ratio of, again, just over 0.706, and we see very good equilibrium between the minerals within the eclogite and the minerals within the garnet amphibolite, equilibrium shown by those minerals falling very nicely along this line, and having an initial strontium value that is almost identical to the white mica-rich veins that intruded the original rocks. So what does that tell us? That these white mica-rich veins intruded the amphibolites, and that those veins were responsible for growing the eclogite facies minerals. There are other places like this around the world, and one is in the Bergen Arcs in Norway. And this is Håkon Osterheim, who was one of the first people to recognize this kind of localized transition in metastable rocks. So in this case, the original rock was a granulite, so comprised of pyroxenes like augite and anarthitic plagioclase. And fractures cut across the granulite also brought in an influx of fluids into those fractures, and that allowed a small zone, perhaps 10 to 20 centimeters wide, around those fractures to be transformed to eclogite. That means that the granulite itself was metastable, meaning it had not transformed over to a stable assemblage of garnet and omphacite, that green clinopyroxene, despite the fact the rocks were at the correct pressure and temperature conditions for those minerals to be stable, because there was some kinetic barrier, and again, this kinetic barrier being the fluids that infiltrated along the fractures. Why does it stop at 10 or 20 centimeters around the fractures? Probably because the fluid was consumed entirely by those reactions. So to help you see it better there's that narrow zone of eclogite formed within the host granulite. There are other places too, further north in Norway. This is in the Loften Islands, on an island called Flakstadøy. And here again, we see small fractures, and here they're defined actually by this black vein of pseudotacholite, which is a glass that is formed by friction, in this case, seismically induced friction, that is, during earthquakes. So small earthquakes occurred and broke these high-grade gneisses, and the heat was high enough to produce a small vein of melt. When that earthquake occurred, it opened up a small pathway again for fluids to infiltrate and to transform a small zone around that fracture to eclogite. You can see the eclogite a little bit better here, at least the green hues, the green and red colors within the eclogite shear zone and the host granulite. I measured oxygen isotopes for the minerals within the amphibolite and within the eclogite and the gabbro and the eclogite, and found most minerals fell between 3 parts per mil O18 and 11 parts per mil O18. And what you're seeing is different minerals plotted with a different symbol within individual rocks. So here's one set of minerals within an eclogite, and there are a couple of muscovite grains analyzed, an omphacite grain analyzed, and quartz. And the reason that you're getting different values between those sets of minerals is simply fractionation between the minerals. You also see mean oceanic basalt at about 5.4 per mil. Those values are shown here in the red swath, and those values are quite typical of metamorphic rocks, and also quite typical for a range of fluids that may have infiltrated those rocks to cause the transformation to eclogite. Notice that these are all positive values of delta O18. Other studies, for example, another area looking at oxygen isotope values in zircons from an eclogitic subduction zone terrain, this time in eastern China. Those values are all very negative, quite unusual for metamorphic rocks. Here are these values for those Chinese eclogites. You notice they're all less than 0, and so depleted in O18. And clearly this time, that's a result of meteoric fluids infiltrating the rocks and being responsible, at least, for the crystallization of those zircons, and probably other minerals in those eclogites. And makes an argument for either metamorphic fluids or magmatic fluids having infiltrated the Marun-Keu rocks in the polar Urals and causing those eclogites to crystallize. If we look at delta O18 plots of different mineral pairs, here and here, versus garnet and omphacite, to consider equilibrium. And what we're looking for is for the fractionation between those mineral pairs to fall along the same line. So the difference between the delta O18 value of a garnet and quartz, or the difference between the delta O18 of an omphacite and quartz, being consistent in these plots, that is, falling along the same line. If those mineral pairs were not in equilibrium, they would fall on some slope much different from the lines representing fractionation between these mineral pairs. And we see pretty good consistency between garnet and quartz, between muscovite and garnet, between omphacite and garnet, between amphicite and quartz, and muscovite and quartz. So that's further evidence, in addition to the rubidium-strontium isotope evidence, that the quartz mica veins are in equilibrium with the eclogite, here reflected by the amphicite and the garnet. So this is the way to use oxygen isotopes to establish equilibrium crystallization of different minerals. And we can also use the O18 values of different mineral pairs to calculate temperatures. And so here we've got quartz and garnet following along fairly consistently a line that represents 650 degrees Celsius. And here for quartz and amphicite representing also 650 degrees Celsius. And that's consistent with eclogite facies temperature conditions. So again, more evidence that there's equilibrium between the vein minerals and the minerals within the eclogite, and the temperatures that are consistent with eclogite facies metamorphic conditions. And those temperatures are calculated relating the fractionation between different mineral pairs using these constants A and B that are shown in this table, and temperature. This is another set of plots that also assesses equilibrium. And what you should see is between garnet and amphicite, this is the amphicite in the triangles and the garnet in the squares. They fall on these arrays between about 600 and 700 degrees Celsius, consistent with the last plots. And a bit of disequilibrium is shown by the fact that muscovite, in sample J12A at least, is not falling on the same array as amphicite. And so there's incomplete equilibrium in these rocks, demonstrated by these oxygen isotopes. Here's another example from a different sample, also showing equilibrium between the garnet amphicite, and here between garnet and muscovite. I wanted to demonstrate the use of these oxygen isotopes to show both isotopic equilibrium, crystallization of different minerals, and of calculating temperatures for mineral growth in these rocks.